Welcome to College Algebra. In this lecture video, we are going to talk a little bit about how to solve logarithmic equations. So in the previous 5.5 video, I show you how to solve these exponential equations involving with two terms. So let us take a look at how we can solve the log equations. So couple properties that we mentioned before back in 5.4, the properties of logarithm. When we have multiplication, a log of base a of m times n, we can expand it into addition. Okay, if it's a division of logarithm right here, we can actually expand them to subtraction. So now we also did some example where we take the two terms and actually put them back into a single logarithm before. We're going to use these properties now to help us. Okay, so ultimately, for example, this problem, what I want to do is make these two terms of logarithm back into a single logarithm. What I want to see is a log on one side and the other side does not have a logarithm. Okay, so in that case, we can use our change. We can actually change our logarithm into an exponential function. So real quick, the subtraction here, make this back. Rewrite this back to a single logarithm. That would be log with the base 4 of x plus 2 over x minus 4. Okay, equal to 2. So basically, what I want to see is one term with a log, another term don't. Because in that case, all right, if I will go back, excuse me, if I'll go back to 5.3, when we're talking about the properties of logarithm. All right, so when we're talking about conversion between exponential equation and log equation, one thing I did not really mention is this right here is actually two terms, but one of them has a logarithm. So what I can do is convert my logarithm into exponential. So when I see these problems, that's what I have in mind ahead of time. So moving my base 4 to the other side, convert them into exponential, and I get x plus 4, excuse me, x plus 2 over x minus 4 equal to 4 to the second power. And we know 4 to the second power is the same thing as 16, so I'm going to go ahead and write 16 here. Alright, so 16 being 16 over 1, to solve for x, I can use my cross product. Okay, 1 times those two terms on top will still be x plus 2. Set it equal to 16, multiply those two terms down there. So 16 times x is 16x. 16 times negative 4, negative 64. Alright, so what I got myself here is a linear equation. So move my x over, that gives me 15x equal to 66. So my answer, x equals 66 over 15. I think I can reduce that. So that will be 22 over 5. Okay, so that's how we do these problems. Alright, remember now, I keep on saying natural log is the same as a log. The difference between this problem up here and this one is these two terms, both of them contains a logarithm or natural log. This one up here, where you have one term, does not have a log. So when there is one term don't have a log, you can actually convert them into exponential. If all the terms, contains natural log or log, then we can use the property of logarithmic equality, where it says when the log are the same and equal, we can set what they are of equal to each other. So that means I got two natural log equal to each other, so I can set what they are of equal to each other. So that gives me x minus 5 is equal to x. Okay, so move this x over, so that gives me 7x equal to negative 5, and divide both sides by 7. My answer x equals negative 5 over 7. Now, unfortunately, if I were plugging x as a negative, that will make me take a natural log or any log of a negative number, which, as I showed you before, is not a real number. So that means this cannot be my answer. Okay, so this problem, I have no solution. Alright, so some of these problems is like that, where you got no solution. Alright, let's look at another similar one. Alright, all three terms contains with log. So all I gotta do is make these two terms on the left side into a single logarithm equal to another log, so I can set what they're of equal to each other. So by having a subtraction sign here, I know this is going to be log with the base 3 of 2x plus 1 over x, set it equal to log with the base 3 of 5. Alright, now I set what they're of equal to each other, and I can use another cross product. So 5 times x, 5x, set it equal to 1 times 2x plus 1 is 2x plus 1. So move my 2x over, that give me 3x equal to positive 1. So my x equal to 1/3. Alright, by looking at this 1/3 and plug into my equation, I think 1/3 will make everything positive, so this will be my solution. Alright, so one term don't have a log, convert them into exponential. When all the term has log, we can actually set what they're of equal to each other. Once I actually brought them down to one term log equal to one term log. Alright, now this one, again, 3 terms. Okay, this is a plus sign. So a plus sign means back into a single logarithm would be multiplication. So that would be log with the base of 6 of x plus 4 times x minus 4. Okay, set equal to log with the base 6 of x plus 14. Alright, so let's set what they're of equal to each other. And when I do that, as you can see, these two need to be multiplied out, which will give me x squared. So I actually gonna end up with a quadratic equation. So I'll go ahead and skip the step where I set them equal to each other. I'll go ahead and multiply them. Difference of square will be x squared minus 16 equal to my x plus 14. So this is a quadratic equation. So I'll keep my x squared positive, move my x over, 14 over. That will be x squared minus x minus let's see, negative 16, negative 16, negative 30 equal to 0. Okay. For 30, I will probably use 6 and 5. Alright. Since the last sign is negative, since the last sign is negative, one is positive, one is negative, to end up with a negative 1 in the middle, I gotta have a negative 6, positive 5 in the middle. So my answer, x equal to 6 and x equal to negative 5. Alright. Now if I take this negative 5 and plug into these x's, okay, I will actually end up with a negative in one of these parentheses. So I cannot use a negative for answer. Alright, 6 plus 4 is positive, 6 minus 4 is positive, 6 plus 14 is positive. So 6 will be my answer. Alright, that's how we solve some of these logarithm equations using the properties that we learned previously. Alright, now the very last thing I want to go over with you in this chapter 5 lecture video series is wrapping up with some kind of with some of these exponential decay or type of problem, application problems. So we talked about exponential decay type of problem before, but these problems are a little bit different because the base for these following examples are all using base e. Okay, so let me kind of show you how to do this. Some of this is not hard. Our function, our decay function, the only thing different is now my k. Okay, this go way back. I don't talk much about this k because the k is really occurred when I'm using a base e. So if I go back to 5.1, okay, with a population growth function, okay, where is it? Oh, excuse me, 5.2. Sorry about that. Okay. So we have two different functions: p sub null times base a, growth rate a to the t power, or I can use a base e to the kt power. So the k is called the exponential growth when it's positive. When it's negative, it's called the exponential decay. Okay, that's what we're having here. So this negative 0.0043 is actually a k. My k is actually negative. So A sub null is the initial amount. Okay, a radioactive substance decays according to this function, where capital letter A is how much of the substance that is left after some time t. All right. T is a time in years. So if my initial amount is 160 grams, find the time for the radioactive substance to decay to 103 grams. So that means I want to decay down to 103 grams. That is equal to initially started with 160 grams times e to the negative k times t power. So the question asks me to find the time it takes to decay to 103 grams. Okay, so we've seen similar example like this before, and I did mention the process how to solve this is very similar. First thing, get rid of this 160, the initial amount, by dividing both sides by 160. And I never really divide it here. I just go ahead and roll it here before. So I'm going to do the same thing. 106 over 160 is now equal to e to the negative 0.0043t. Alright, so now I got two terms. Okay, to get rid of my e, we can take a natural log on both sides. So now this problem look just like some of these problems that we done in a part 1. Okay, where if I have an e, if one of my terms contains e, we can take a natural log on both sides. Alright, take natural log on both sides. So the right side, the natural log and e will cancel out. So this is what's left over, which is negative 0.0043t. Alright, equal to the natural log of 103 over 160. So to get t by itself, now all I gotta do is divide it by my coefficient, negative 0.0043 on both sides. So in the calculator, I want to type in this first, natural log. Okay. Natural log is one term, 103 over 160. Close the parenthesis for the 103 divided by 160. Now I'm going to divide it by my coefficient, negative 0.0043. My time. Run to 2 decimal place. That will be 102.43 years. Okay, it will take that many years, because t was in years, I believe. Yeah, it will take that many years to decay down to 103 grams. All right. Let's try another one, okay? This problem is slightly different. This problem, okay, does give me a exponential decay, but it says SNO is the initial amount, time is in hours, determine the half-life of the substance, okay? It basically wants me to find the time it takes to decay down to half-life. So what does that mean? I mentioned this before. Decay down to half-life means half of its initial amount. Okay, so after some time t, what I should end up with is half of its initial amount. So half of its initial amount is equal to the initial amount times e to the negative kt power. Okay, so right away, the process of solving for t, okay, or solving for k, is the same. Divide both sides by your initial amount. So all you got now is a half equal to e to the negative kt power. So just like the previous problem, to get t by itself, I will need to take a natural log on both sides, because natural log and e will cancel out. So the only thing I got left with here is negative 0.04t equal to my natural log of a half. So now to get t by itself, I just divide both sides by negative 0.04. Alright, so in my calculator, I'm going to do natural log of a half. Well, I'm just going to say 0.5 divided by negative 0.04. Okay, so my half-life, okay, will be 17.33 hours. Okay. All right, this problem is a little bit easier because where seasonal is an initial dosage of a drug, okay, concentration of a drug in the body fluids, okay, it's an exponential decay because once the concentration is in the body, eventually it wears off. That's why it's an exponential decay. All right, so if it's 25 milligrams of a drug given, that's my initial amount. How much time elapses until 11 grams remain? So 11 grams goes here, 25 milligrams goes here. Looking for the time to decay to 11 milligrams. Okay, it's not a problem. So this problem is very similar to this one right here. Basically the same thing, just a different topic. So divide both sides by 25 first, take a natural log on both sides. So eventually I will have a natural log of 11 over 25 is equal to negative 0.8t. So to get t by itself, we will just take natural log of 11 over 25, then divide by negative 0.8. Okay, so that would take about what t was in. hours. So it'll take about 1.03 hours. Okay. All right, now the next problem is actually very similar to this one, the half-life one. Okay, but asking for a different thing. So the model for radioactive decay is in this function. Okay, a radioactive substance has a half-life of 50 years. Okay, so this time it tells me what the half-life is. If 65 grams are present today, how many years will 30 grams be present? So what the problem does not give me is the K. The problem is asking how long it will take to decay to 30 grams. Okay, but it does not give me a K. So the first thing we got to do is actually find the K. Okay, half-life is 50 years. So that means half of its initial amount is going to equal to its initial amount times e to the negative k, k is unknown, times t, which is 50 years. 50 years become half of life, half of initial amount. So previous problem here, we're solving for the time of half-life. Now we are actually looking for the decay rate by given the half-life. Okay, so the computation is very similar. Divide both sides by Weiss and null. So that leaves me with half equal to e to the negative 50k. So now I will take a natural log on both sides. So that leaves me with natural log of a half equal to negative 50k. So now to find my decay rate, we will divide both sides by negative 50. Natural log of 0.5 divided by negative 50. So we're on to 7 decimal place. My k will be 0.0138629. Okay, 1, 2, 3, 4, 5, 6, 7. The 4 will make my 9 stay the same. 138629. Okay, so that's it. So that's just the k. That's just the k. So that means my model itself is y equal to Weiss and null times e to the negative 0.0138629t. So basically, when they give me that half-life of 50 years, is information that helped me to find my decay rate k. So once I got my k, I actually have my whole model. Now I can answer the question. If 65 grams are present today, so initial amount is 65 grams. Okay. How many years will go down to 30 grams? So the time. So the problem is looking for time. 8629. Okay. So divide both sides by 65. We'll take a natural log on both sides. So then I will end up with natural log of 30 over 65. Okay, the process is the same. Equal to, so divide, 65. Divide 65 on both sides, take a natural log on both sides, the e will cancel out, so that just leave me with my negative kt power to 9t. That's a lot of digits to write. Alright, so to get my time by itself, we'll divide both sides by my negative k. So that would be natural log of 30 divided by 65, close parenthesis, then divided by negative 0.0138629. Okay, so that will take about 55.77 years. Okay, that will be my answer. Alright, so that will be all for your exponential function and its inverse, the logarithm function and its properties. Alright, thank you for watching.